Let me start by saying a few words to welcome everybody today. In particular, the leadership within the Department of Energy's Office of Science that are here joining us today. Dr. Geraldine Richmond, the Undersecretary for Science and Innovation, is on Zoom. The Deputy Director for Science Programs, Dr. Harriet Kang, is right here, as well as leadership from HEP, welcome Gina, and BES, BER, and a number of other programs. So I really appreciate everybody joining us today. I also want to thank the National Lab directors that are in attendance, the teams that put together the nomination, I think really important, all the folks that were involved in peer review, and of course, the fellow herself, her family and loved ones and invited guests who are joining us in folks who are here in person, as well as everybody that is online. I am Asmarit Asifal-Berhe, the Director of the Office of Science. But before I go any further, I want us to take a moment and pass the podium, if you will, virtually to the Undersecretary for Science and Innovation, Dr. Geraldine Richmond. Jerry, all yours.
Okay. Great. Well, good afternoon, everybody. And for some reason, I'm completely blanked out. The video isn't quite working, but I just want to say I'm smiling here with a big congratulatory giggle on the side. Just to let you know, you can't see it, but that's where I am. So good afternoon to you all. I am indeed Jerry Richmond, the Undersecretary for Science and Innovation at the Department of Energy. And it is my pleasure to join you today and congratulate Dr. Marcela Carena of Fermi National Laboratory for her selection as a 2022 DOE Office of Science Distinguished Scientist Fellow. Boy, do I wish I could be there, but at least you can hear my voice. To be able to speak at like an event is a joy for me, and to also celebrate the amazing scientists we have at our labs. And so, as you will hear from Dr. Berhe shortly, Dr. Marcela represents the best of DOE with over 25 years of scientific leadership and service at the National Laboratory and the international high energy physics community. Dr. Carena and all the distinguished scientist fellows are why Secretary Granholm calls DOE America's Solutions Department. They're strengthening American leadership and competitiveness in science, technology, and advancing diverse fields in discovery science. Fundamental groundbreaking science is baked into the DNA of DOE and to our success as a nation. So I look forward to hearing from Dr. Marcela Carena today, and please join me in a short round of applause and hoot and holler for Dr. Carena. So I'll turn this back to you, Dr. Berhe.
Thank you, Jerry. I think it's not an exaggeration for me to say that it is moments like this that are among the most fun aspects of this job, right? It's a huge honor for me to celebrate not just the discovery mission of the Office of Science and all the great things that we accomplish in the science and technology space, but then at the same time be able to celebrate the scientists that make that possible. And these accomplished scientists that are funded by DOE that we get to brag on, really. And allow me to do a little bit more bragging on Dr. Carena and just speak a little bit about the events that brought us all together today. I think it's extremely important that we recognize the impact of the research that we do, or the research that we enable through the Office of Science, and we share that with everybody as much as possible, right? As we're trying to do today. And it's really wonderful to see the large crowd assembled, not just here, but also on Zoom to join us for today's event. So it's moments like this that make it just so important for all of us to take a pause and reflect on what can be done when the administration as a whole and Congress provide robust and long-term support for the science that we all love. So on October 26, 2022, the Department of Energy announced 2 National Laboratory scientists as the 2022 Department of Energy Office of Science Distinguished Science Fellows. One of them, who's here with us today, is Dr. Marcela Carena of Fermi National Accelerator Lab. And the second one that we all heard from a few weeks ago was Dr. Sheng Dai of Oak Ridge National Laboratory. I am really thrilled to be here with you all today to honor and introduce one of the two 2022 fellows, Dr. Carena, a theoretical physicist and head of the theory division at Fermi Lab. She is also a professor of physics at the University of Chicago, and an amazing and influential researcher with a long track record of inclusive science practices and science, who's just had an incredibly impressive list of accomplishments. I'll try to get into a few of them today, but really we won't do that justice because we want to hear from her for the most part. So today's event, of course, is the second lecture of the two-part series that we're featuring the 2022 Distinguished Scientist Fellow winners. And I encourage everybody who's joining us today to visit the award program website at science.ost.gov for additional information on the award and their work, including where you will find a link to the first lecture that Dr. Dai gave here, right here in the room, not that long ago. And before I present the award plaque, and before we get on to hearing from Dr. Carena, I want to add a few words about what the program is that we're talking about, the Distinguished Scientist Fellows Program, and how we arrived at the Office of Science at the 2022 winners. So far, we've honored 13 fellows, including the 2022 cohorts in particular, since the award was first bestowed in 2019. Each fellow receives $1 million in direct funding to be used to support activities that develop, sustain, and promote excellence in Office of Science research through collaboration between institutions of higher education and national laboratories. These awards are intended to honor the extraordinary scientific achievement and professional service record of senior scientists at DOE National Labs. They also strongly promote scientific and academic excellence in Office of Science research through collaborations, as I mentioned, with academia and other labs. So to accomplish this, then to run through the competition, nominations were solicited from all of the 17 DOE National Laboratories, and the two 2022 fellows were selected based upon a very rigorous internal and external review process and received my full endorsement as the Distinguished Fellows. Both Dr. Carena and Dr. Day represent excellence in their field and now join the growing community of fellows that will present the best of what we do with the national labs and what we have to offer to science, mentorship, and service across multiple areas. Now I'm going to pause a little bit here and tell you a little bit about Dr. Marcela Carena's accomplishments and her bio. It's my honor to tell you about a featured fellow today, of course. Dr. Marcela Carena is honored for leadership and influential contributions to particle physics. These contributions include novel theoretical ideas and strategies for HEP experiments related to the Higgs boson, dark matter, electroweak, baryogenesis. That one is fun to say. In addition, Dr. Carena has been an unabashed promoter of Latin American participation in DOE-hosted experiments. At the time of her nomination, the then Fermi Lab director, Dr. Nigel Locklear, said about Dr. Carena, "I enthusiastically endorse the nomination of Marcela Carena. She is an internationally renowned scientist who has helped shape the experimental program at Fermi Lab for the past 25 years. Her leadership of theory division has greatly benefited the DOE mission, and she's a mentor and role model for junior scientists from diverse backgrounds." I think if you look at her record, you will totally agree with that. And of course, I completely do. Dr. Carena is an internationally recognized leader in her field. She pioneered many studies of the Higgs sector of the Standard Model, including dynamical electroweak symmetry breaking, gauge coupling unification, Yukawa coupling unification, and infrared fixed points of the top Yukawa coupling. In October 2021, she authored the cover story of Scientific American on the exciting results of the muon G-2 experiment, and Professor Carena has given more than 300 invited plenary talks and colloquia at conferences, universities, labs, and around the world. So it's clearly in high demand. So we're really honored that she's going to take the time to speak to us today. In her innovative research, Dr. Carena explores the possible connections between the Higgs boson, dark matter, and the origin of matter in the early universe. Her research has exposed the power of precise low-energy measurements for the exploration of physics at energies much higher than the collider experiments can conceivably reach. She's been a leader in exploring radical new concepts. Her deep understanding of electroweak symmetry breaking enabled Dr. Carena to develop highly influential models of electroweak baryogenesis to explain the matter-antimatter symmetry in our universe. In all her work, Dr. Carena has concentrated on identifying experimental signatures that, if seen, would validate the predictions of her models. More recently, she performs research at the boundary between particle physics and quantum information to tackle problems of quantum theory and the early universe. The research Dr. Carena will pursue with the Fellowship Award will explore possible connections between dark matter and electroweak baryogenesis, with an emphasis, as always, on identifying detectable experimental signatures. In addition, this new work would leverage the power of quantum simulations to study effects that cannot be addressed with simulations on classical computers. Beyond her tremendous contributions to the field of science and the national laboratories, Dr. Carena is an accomplished and inclusive leader. She provides a level of service to the international research community that for most other people would constitute an entire career itself. She leads multiple research groups at Fermi Lab and at the University of Chicago. She's been recognized by her peers through fellowships, awards, honors, and professional leadership positions. Really, as I said earlier, way too many to list and talk about here. But I'd like to hone in on Dr. Carena's impact at home and abroad, particularly in the area of supporting early careers, researchers overall, and students. It cannot be overstated that when you ask accomplished scientists what motivates them, right, they're likely to mention one more mentors that played an important role in their careers. I was very lucky to have several strong mentors, and I think, like most people, would really, really aspire to see everybody have that kind of strong mentorship support. And so I really have an appreciation for these relationships and the way they can change the lives and career trajectories of early career researchers. And so Dr. Carena embodies a strong commitment to improving diversity, equity, and inclusion, both at Fermi Lab and more broadly across her field of high energy physics. She has supervised numerous graduate students and undergraduate students into their research. More than a decade ago, she established a Latin American student program at Fermi Lab that's been bringing students from across the continent, including Argentina, Brazil, Colombia, Mexico, and Peru. They collaborated with Dr. Carena and other scientists at Fermi. Dr. Carena also founded a summer program for underrepresented undergrads and the Sylvester James Gates Junior Postdoctoral Fellowship, where she's specifically targeting outstanding researchers from underrepresented backgrounds in STEM. Dr. Carena herself, though, represents also the attributes of an Office of Science Distinguished Scientist Fellow: commitment to science and excellence, leadership, and service. She has published over 160 peer-reviewed articles that have already been cited more than 62,000 times. And as I mentioned, delivered over 300 presentations at all sorts of colloquia and conferences and public lectures around the world. And it's super impressive, right? List of accomplishments over her distinguished career. And of course, there's a lot more to come, right? she's on it. There's still a lot more to be done. And so I want to take another pause here so that we can present Dr. Carena with her award. And so let me say again, congratulations, Dr. Marcela Carena. Your accomplishments are tremendous. And so you all can join us. So I'd like to invite Dr. Harriet Kang, Office of Science's Deputy Director for Science Programs, So please join me here in presenting this award to Dr. Marcela Carena, and who's joining us up front. It is our incredible pleasure to present this award today to Dr. Marcela Carena for her leadership and influential contributions to particle physics, including novel theoretical ideas, strategies for HEP experiments related to the Higgs boson, dark matter, and electroweak baryogenesis, and promoting Latin American participation in DOE-hosted experiments. Please join me in giving Dr. Carena a huge round of applause. Yeah.
Yeah. I think there was a picture of the three of us.
This one is my easy. Perfect.
Okay, thank you. Thank you.
So before I conclude my remarks and hand the podium over to Dr. Marcela Carena, I would just like to say a final congratulations, Dr. Carena. It's really an honor for us to celebrate your accomplishments and your work today. And I also want to say thank you to all of my Office of Science colleagues who are participating in the ceremony, and members of the audience joining us today, both in person and virtually. Special thank you to the HEP, Office of Science's High Energy Physics Program, the Office of the Deputy Director for Science Programs, and the Office of Communication and Public Affairs for hosting this event today. So please, everybody join me in welcoming Dr. Marcela Carena to the podium for her lecture entitled Early Universe Phase Transitions, Baryogenesis and Signals at the LHC, which I should say will be followed by a Q&A session with the audience after all. Dr. So now you're good.
So good. Oops. Okay, so first of all, thank you, Dr. Berhe, and thank you, everybody. I'm truly honored and humble for receiving this award, and I will talk about early phase transitions and baryogenesis and signals at LHC, which represents an important part of my research that is related to this distinguished scientist Fermi. So I will start again thanking once more to the so many people who made this award possible. My mentors, of course, brilliant postdocs, students, and junior colleagues, and also all my Fermi Lab colleagues and collaborators from all around the world. Very special thanks go to the DOE Office of High Energy Physics for your support and encouragement, both of my research and of the career development of the students and postdocs who are the future of our field. And last but not least, I want to thank you, my family and close friends, for their support, patience, and for making the journey worthwhile. So this is a picture of Fermi Lab theories going back at the pandemic. So this was like early last year. Only 2/3 of the people are there, and you see a lot of happy faces because we were so happy to be back. Okay, so let me start reading from the webpage. The mission of the Office of Science is to deliver scientific discoveries of major scientific tools to transform our understanding of nature and advance the energy, economic, and national security of the States. So today I will start with an important scientific discovery, the Higgs boson, and the world's largest scientific tool, the Large Hadron Collider. So I will talk about my research that builds on this game-changing discovery to transform our understanding of our origins. So this is the phase transition instant after the Big Bang, our universe, made of dark matter. We want to know what it is. And some of the biggest mysteries, so why is more matter than antimatter? So we are about 10 years after the discovery of the Higgs boson. That was the discovery of a new type of particle never seen before that proves the existence of an invisible energy field. So about almost 60 years ago, Mr. Higgs proposed a system of a Higgs field that turns on at instants after the Big Bang, and in that way gives masses to the gauge bosons, the W and the C boson. In fact, these ideas are coming from, so this idea of the Higgs turn on, we call it spontaneous symmetry breaking, are ideas that come directly from condensed matter physics ideas. And as Peter Higgs says here, the phenomenon is just this phenomenon of a Higgs boson turning on and giving masses to the gauge boson is the analogous of the plasmon phenomenon in superconductivity, to which Anderson drew attention many years ago. So here, this is the reception at the Nobel Prize ceremony, and Mr. Higgs is telling me and my friend Fabiola that his first paper was rejected because it was not relevant for real physics. What he said. So he said, in the first paper, in the first version of the paper, I talk about the invisible energy field. In the second version of the paper, I said, okay, if you want to prove the existence of the invisible energy field, go and look for the Higgs boson. So we did look for the Higgs boson and we found it. And for that, we required the largest, most complex scientific instrument ever built. That means the Large Hadron Collider. And you know that your instrument is really big when it's super big compared with an international air. So in order to make this discovery, we had to build the most powerful cameras ever built. These are our detectors, and in particular the CMS and Atlas detector. And you see a beautiful picture of the CMS detector here. So DOE has been deeply involved in the discovery of the Higgs boson. Fermi Lab is the host laboratory for the US CMS collaboration. And in fact, Fermi Lab has the largest CMS group after CERN, and there are another 49 US institutions that are part of CMS. And here we have, very proud, our Fermi Lab distinguished scientist, Paddy McBride, which is the newly elected spokesperson of international CMS collaboration. Other 4 DOE labs participate in the other big experiment, US Atlas, with another 41. So why this is new today is because Run 3 is just starting. Okay, in fact, this is Fabiola around July 2022, saying that the first collisions you see here, I don't have a pointer, but you see here the first collisions on July 2022 at 13.16. Run 3, more and better. There are a lot of things that are much better, and in particular, let me say that is cutting edge artificial intelligence hardware and software that we hope will enable models. So what to expect? So before going into what to expect, let me pause for a minute and say the great success of the Higgs discovery. So since 2012, we have measuring with increasing accuracy the properties of the Higgs boson, and the study of its properties had provided what we say is the first portrait of the mechanism of electroweak symmetry breaking. And you see it here, this is the mass of the particles, and this is the strength of the Higgs cupping to those particles. And in fact, the mass of the Higgs boson ended up being at 125 times the proton mass, or GeV. And it is what we call a lucky spot, as you will see in the second part of this talk. It ended up being lucky for one thing and not so lucky for others. But it's the lucky spot to maximally allow us to measure its interaction with our particles. And that's what we have done here. We have measured the Higgs boson interacting with the gauge bosons and with the third generation quarks and with the second generation muon. And we see that this is the prediction of the standard model. So we see that it's pretty close to the prediction of the standard model. And however, deviations of the order of several % are still possible, and this is things that we are going to measure much better in the next 2 decades. So this is one part of the story, how well we are going to test the mechanism of electron symmetry breaking in the standard model. But the experiments in RAIL 3 also have the power to address new questions about the Higgs boson, things beyond what we mentioned. And let me just show you some questions that I think are interesting to be addressed at LHC. The first question that comes to my mind is, are there Higgs cousins? Are there other Higgs particles? And if so, what are their properties and how do they impact the properties of the Higgs that we have mentioned? It's natural to think, why should be only one guy at the time? The other thing is the Higgs self-interactions. Are they different of the one expected in the standard model or not? If we measure how the Higgs interacts with itself, so far we have measured Higgs interact with other things. But if we measure how the Higgs interacts with itself, we will know a lot about this behavior of the Higgs turning on that Mr. Higgs was trying to explain. Of course, does the Higgs boson violate the charge parity symmetry, which is the fact is the symmetry that makes a difference between matter and antimatter when it's broken. So this is very important. And then the two other questions I want to concentrate on is the Higgs boson related to dark matter? That is one of the big mysteries we have. And for that, we are trying to look how the Higgs could become invisible at the edges. And the other big question is, we know that there is more matter than antimatter in the universe. Is this fact connected to the Higgs boson via this early universe phase transition that broke the electroweak symmetry? So the universe originally was in an electroweak symmetric state. When the Higgs turned on, it broke that symmetry. And at that moment, that we call it the electroweak phase transition moment, does that moment have anything to do with generating more matter than antimatter? Okay? And this will be kind of the main topic of this talk. So the overarching question that really reached all of this is, what is behind the mechanism of electroweak symmetry breaking? We know this electroweak symmetry breaking occurs, but in the standard model, we really engineer it. We put it by hand, okay, by putting the mass parameter negative. So we want to know what is behind it. What is the real theory or reason why that happens? And so this overarching question will for sure shed light to some of these questions here. And in particular, in this talk, I will concentrate on these two issues. Is the Higgs boson related to the dark matter? Is the Higgs boson related to the matter antimatter asymmetry? If we understand electroweak symmetry breaking, the question I want to ask today is what was the history of this electroweak? How it happened? We know it happened instance after the Big Bang, but how it happened? Okay. So this situation, when we say when the Higgs turn on, instance after the Big Bang, is what, as I said, what we call electroweak phase transition. Okay. But how this happened? So I put here a suggestive picture that shows that bubbles of what we call the Higgs on, which is a true vacuum today, are expanding in the fake vacuum, okay, which is the Higgs off. But if this was really what happened, we don't know. So this is a question mark. And we will go back to that. And also, we want to understand if this happened this way, it is related to this generation of the matter asymmetry. And this is exactly the phenomenon that we call, if this relation occurs, we will call this electroweak baryogenesis, which means baryogenesis, or the matter-antimatter asymmetry, was generated at the moment of the electroweak phase transition, at the moment that the Higgs turned on. Okay, good. So we know that there is more matter and antimatter in the universe, and the issue is that we have a lot of measurements that are at different times of the history of the universe, from the time that was what we call Big Bang nucleosynthesis down to the moment of the cosmic microwave background. So this is a long time in the evolution of the universe. And we do measurements of different type there that tells us that the ratio of the baryon number with respect to the total number of photons in the universe is as tiny as 10 to the minus 10. Okay, So the point is, what generated this baryon-antibaryon symmetry, this matter-antimatter symmetry? Was something that was there from the beginning of the universe somehow, or was something that was generated at some moment in the evolution of the universe? So Mr. Sakharov in 1967 was very puzzled by this idea of how to generate the matter-antimatter asymmetry. And actually, this is a very, this is in Russia, someone took that beautiful picture of Sakharov thinking. And so he wrote these three conditions. There should be baryon, and I will explain how later, lepton number violation. Of course, if we start from a universe where baryon and lepton number are zero, and we want to generate something that is not zero, at some point we have to violate it. Okay? The other issue is charge and CP, charge parity violation. This symmetry should be violated because these symmetries are the ones that treats particles and antiparticles, or matter and antimatter in a different way. So we need that violation. And finally, what we call out of thermal equilibrium processes, because what it means is that we have generate something, we have to be able to shut off the system so that it doesn't wash out whatever we have generated. Okay, so basically suppress the inverse process. Okay, so we show that these three requirements can in principle be fulfilled in the standard model of particle physics that we all know and love and has been proven so well. However, although these three conditions are fulfilled in the standard model, in fact, the standard model cannot explain the observed values. Okay. So there are possible mechanisms for generating the baryon-antibaryon asymmetry. The one I will talk today is the electroweak baryogenesis. As I told you, this electroweak baryogenesis is the one involving the Higgs field. There is another leading idea that is called leptogenesis, and this one involves neutrinos. And here, the DOE program, and in particular LBNF-DUM, will do a lot to address this question. So the point is that these are two leading ideas, but we don't know which is the right one. And in fact, we could need at least the next few decades to understand which one is the right one. That's why theories are necessary. So let me, this is not good. Okay. I knew this was going to happen. Okay. So I will go through these three conditions one by one in the standard model. I didn't want you to pay attention to this equation, but please don't pay attention now. Because so in the standard model, baryon number is not conserved at the quantum level. So that's good. And I won't go into details, but the idea is that it was proven long ago by this gentleman, a process called anomalies. That means that gauge theories, symmetries of the standard model, are violated, that which are conserved at the classical level, are violated when we quantize the theory, okay, in the quantization. And what happens is that the chiral weak interactions, that are the ones that are felt by quarks and leptons equally, comparable, because they are gauge symmetries that need to be preserved, they need to be anomaly free. And in the process, in the math of doing that is quite involved, the result is that in order not to have anomalous chiral weak interactions that we cannot have, we need to have the non-conservation of baryon and lepton number. And although this equation doesn't tell you much, it tells you less now, this means that in the standard model, there are going to be processes where the difference between baryons and antibaryons, or leptons and antileptons, is non-zero. But however, the violation of baryon number is always equal to the violation. And this is what I mean when I say B minus L is always conserved. Okay? So any process I have within the standard model will conserve B minus L, but we violate B and L. Okay? And this is what the sphalerons do. The sphalerons are some funny semi-classical configurations. Let me just put it there. There are some interesting objects. I have been thinking about that for the last N years. So these are configurations that involve the electroweak gauge bosons and the Higgs fields the electroweak fields and the Higgs fields. And what they do is they convert quarks into anti-leptons and anti-quarks into leptons. And they do that so that B minus L is conserved. That's why they do this. And they can do that because they can both, these interesting sphalerons, they can violate both baryon and lepton number because they have the property that they can connect solutions of the vacuum that have different baryon. Okay, so these beasts, the sphalerons, are very powerful and are at the core both of baryogenesis and of leptogenesis. We need these sphalerons for everything. So at final temperature, so we are coming from the Big Bang and cooling down the universe. At final temperature, this is the energy of the sphalerons. There is the baryon number violating process, the rate of baryon number violating processes is governed by the energy of the sphalerons over the temperature. And the one thing I want you to think about is that the energy of the sphalerons happens to be proportional to this parameter, B over T, which is the vacuum expectation value of the Higgs, which means the energy of the sphalerons directly gives you information of the Higgs turning on. When the Higgs turns on, this B is different from 0. If the Higgs is off, this B is equal to 0. Okay? So we have these sphalerons, and these sphalerons are going to allow us to do baryon number violation. Right? Number one. Number two, I told you that we need to be out of equilibrium. Sakharov condition number 3. In order to be out of equilibrium, we do have to have this picture, in the sense that we need to have, out of equilibrium means we need to have a first order phase transition, something that happens abruptly and not slowly going from one vacuum to the other. This is what happens here. This is very high temperatures. This is the critical temperature at which the fake vacuum and the real vacuum are of the same potential energy. And this is where we are today. So what happens is in a first order phase transition, I start forming bubbles that form very fast. And then the universe tunnels from an area where the Higgs field is off, which is all this area here, to inside the bubble where the Higgs is on. And if you think about, it's like, you know, if you're boiling water and you have vapor, bubbles of vapor, they start growing and growing and growing, and then they get out. So this is what happens. You have these bubbles growing, 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 and finally, the whole universe is made of this Higgs bond. Okay? And if this happens, there is what we call a first order phase transition. Okay? So there is a little subtlety that is not very important for the talk today, but it's very important for electroweak baryogenesis, and is that the phase transition happens for temperature a little below. So I put this a little below here, a little below critical temperature is the nucleation temperature. It's really when the bubbles nucleate and the transition occurs. And we have to compute that and see. So the last part I want to say that we mentioned is the CP violation effects. I told you number 2 conditions, we need to have CP violation. What this means is that close to the bubble wall, this is the bubble wall, this is where the Higgs is on, this is where the Higgs is off, okay? Close to the bubble wall, the CP violation implies that the wall itself exerts different forces for particles and antiparticles. So the Higgs and the top quarks, for example, close to the wall connect to each other so that there is different forces for particles and antiparticles. And these different forces for particles and antiparticles creates an asymmetry. But the asymmetry we are creating there, we call it chiral asymmetry, because what it means is that the asymmetry is equal in magnitude but opposite in sign for left and right-handed particles. And you will ask me, left and right-handed particles means the spin with respect to the moment of where the particle is moving. They are the same way, it's a right-handed particle, if not left-handed, but we are left and right-handed. An important point here is that, so we are here, And then we have these phalerons, these little things here. And I told you already that phalerons turns quarks into antileptons and antiquarks into leptons because they have to conserve the minus X symmetry of the theory. But because this asymmetry has been changed, this process of killing quarks is slower than this process of killing antiquarks. And at that moment, the phalerons, because of this original asymmetry, and because of doing this process, the point is that these phalerons, because they are they are static configurations that are related to the electroweak interactions, they only see left-handed particles. Phalerons do not see right-handed particles. And so they do this business only to half of the spectrum, only to the left-handed particles. And in that process, they are able to create a real balance. Okay, I know this concept is a bit slippery, but believe me, it's mind-blowing. I hope for you too. So these phalerons create this real baryon asymmetry because they only talk to half of the population. Okay, so I did one part. I said, okay, I have these phalerons. I have the first order phase transition. I have the bubble wall. I generated the baryon asymmetry with charge parity violation that I see today, but I generated that at higher energy. So the next question I should ask is, I generated at high energy, can I keep it until today? And what I have to do to keep it until today is that once these phalerons have done their job, I need to jack them off. Okay, so they don't allow to do the inverse process. Okay, and that happens, and I won't go into details, but I'm happy to answer questions. That happens, you can do this evolution of the number baryon density from the temperature, the critical temperature to today, okay? And I want this to be equal to this, which I want this to be 1, okay? And in order for this to be 1, you believe me, this math, that what you need is that the vacuum expectation value of the Higgs at the critical temperature over the critical temperature, that is related to this quantity here, has to be equal or larger than 1. And this is the condition of a strong first order phase transition. So I need a first order phase transition and CP violation to generate the baryon asymmetry. And I need that the first order phase transition is strong in order to keep it until today. Okay, so these are the two conditions for baryogenesis. Enough CP violation to generate the baryon asymmetry and a strong first order phase transition to keep it until today. Okay, good. Oh, sorry. So I told you the failure of the electroweak baryogenesis in the standard model. Okay, and in principle, the standard model was all ready to go. Okay, first Sakharov condition, baryon number violation, yes, checked. As phalerons are there. CP violation, yes, because there are 3 generations of quarks, is that we can have CP violation in the standard model. And so you would say nature gave us 3 generations of quarks to have CP violation to be possible to make baryogenesis, electroweak baryogenesis. But it happens that the amount of CP violation in the standard model and the way it happens is too small in order to generate by 10 orders of magnitude the desired balance. So it really doesn't work. And this was shown by my good friend Belen Gabella many years ago. Well, the discussion was like 10 years later, we were still discussing about these calculations because these calculations are super, super detailed and careful. So the standard model, this one is not checked. There is CP violation, but let's say it's not enough. Okay, and the third one is the non-equilibrium. Okay, we have the electroweak baryogenesis standard model, but is it a first order phase transition? And the answer is no, because the Higgs boson is too heavy. So 125 is great to see the Higgs boson talking to a lot of the other particles, to a lot of people. But in fact, detailed lattice calculations shown that if the Higgs boson mass would be 75 GeV or lower, then we could have a first order phase transition. But because the Higgs boson is somewhere here, there is no first order phase transition. So the standard model does not have enough CP violation to generate the Fermi symmetry, and does not have a first order phase transition to keep it. So, no. Okay. So it's clear that if this idea of electroweak baryogenesis works, we need new phenomena. Okay. Well, new phenomena means some combination of new particles and new forces, and nothing is bad about that because we already know that to explain dark matter, we need something new particles and new forces. So that's the idea of this work or this program that I have, is that I'm trying to say I need new physics, new particles, new forces to explain dark matter. And the idea is I want to try to use these new particles and new forces to also make electroweak baryogenesis work. And so I'm going to try to walk you through two cute examples of how it works, how easy it works, how complicated it is to make it work. Okay, so this is the first thing I'm doing here is I'm going to do the minimal perturbation to my Higgs potential. So this part here is the Higgs potential of Mr. Higgs with the scalar Higgs, okay? And now I am adding a singlet. A singlet means that something has no charge, doesn't see any of the symmetries of the standard model. Okay. So I'm going to ask a singlet, and the important part is I'm going to ask that the singlet talks to the Higgs through this lambda mixing. And this is work I have done with my amazing student at U Chicago, Equin. This was, you can see what it was, the graduation, and we were both very happy. And Jen, who actually was a student, which came with a great exchange program supported by DOE from University of Pittsburgh. Okay. And is now a professor at University of Minnesota. So we start with this extra singlet. We are going to break this potential with what we call a spontaneous C2 breaking. Why is this interesting? It's because we are thinking that this singlet can be directly entangled to be a Higgs boson-like particle in a dark sector that is going to break the dark force that is connected to them. Okay, so we have this singlet, and of course, I told you I want to see how things work when the universe cools down, temperatures go down from the Big Bang until today. Okay, and so what happens is I need to not only consider this potential, but I also need to consider temperature corrections, temperature effects, and quantum effects with this potential. And the one thing I want to share with you that is interesting is when I do this simplified version of this potential, I see here that there is a term that is the temperature dependent that goes like a cubic power of this Higgs. And this term is what was giving me this, this was giving me this behavior. Okay, so there is this tunneling that goes through this behavior here that will not be the case without the temperature of this HQ. Okay, so it gives me the barrier. So I was find the word. So I generate a barrier because of the interactions of the singlet. And as a result, you see here, and now I'm looking at the parameter I'm interested to be larger or equal 1 to have a strong first order phase transition. And I can have that this value can be larger than 1. Okay. And the important thing about this is the minimal perturbation I could do to my Higgs theory. Just add C2. Okay. If I do that, there are a couple of things that are interesting. Now this V over T critical needs to be larger than 1. In order for this to be larger than 1, of course, I have to make this a small, but this is dependent on this mixing term. So the larger the mixing between the singlet and the standard model Higgs, the easier it is to get a first order phase transition. We want to get a first order transition, and the easiest it is. However, let me remind you that we have all these amazing measurements of LHC of properties of the Higgs. So we have to constrain how much this Higgs is talking to the singlet. Okay. And the other thing, if we put these in terms of the parameters, so these are the physical parameters, so masses that I can measure and mixings that I can measure. If I do that, then what I see is that the lightest is this scalar, the easiest is to make this B over T critical larger than 1. So I need large mixing light scale. If the scalar is light enough, this is cute because the Higgs can go into 2 of these scalars. And the way I look for this at the Large Hadron Collider is through exotic decay levels. I mean, exotic is Higgs I'm not expecting to see in the standard. Okay. And so what this means is that exotic Higgs decays at LHC are a potent probe of singlet extensions that will allow for electroweak. And this is what we are doing at LHC. There are a lot of searches at Atlas and CMS looking for these Higgs going into these scalars and then going into 4 botons, for muons, taus. So this is for the experts, but you are looking for things, all these decays of the Higgs will not appear in the standard model. Okay. And in a nutshell, let me say that I won't go into the details, but let me say that if you have this, how much the Higgs decay into this exotic into these scalars versus the mass of the scalar, this area here is all the area where you can have a strong first order phase transition and baryogenesis model. And all this area here is what the high Lumi LHC will be able to test. So we are going to probe even this very simple model. I will go back to now, but because of time, probably I would say that because we have a first order phase transition, a first order phase transition implies the existence of a stochastic gravitational waves. That means a stochastic is not the primordial transformation. It generates gravitational waves as a byproduct of the double collision. Okay, so I will come back to that in my other example. So let me now go into the last example. I lost time with time, but I hope I'm reasonably okay. Okay, so a new force in nature. Okay, so this is the fully charged model. It's very difficult, so I will only walk you through it, okay, very fast in 2 slides. So the idea is, I told you, we need a strong first order phase transition. I show you a case where we can go do it. We need enough CP violation in order to generate sufficient baryogenesis. However, there are amazing experiments called electric dipole moment experiments that are constraining how much CP violation can be in nature. And the ACME experiment in 2018 tells that this electron electric dipole moment is constrained to be something like 10 to the minus 29 electron times centimeter. Okay. In a normal theory of baryogenesis, if the CP violation is in our world, so to say, okay, or our sector, then you expect to have something of this order. And this is the amount of CP violation. But most models, to give you the sufficient baryon asymmetry, will have to have this that is larger than 10 to the minus 2. So this means that this is also already going to be excluded by experiments. And what this means is that if you want to make sufficient amount of CP violation to make electroweak baryogenesis, you need to be innovative. And the innovation we are doing in this work is we are putting the CP violation in a dark sector, in a sector that is secluded from ours. Okay, so basically, we are creating CP violation, and let's don't go into all these. We are creating CP violation by some agent that is not talking to any of the particles of the standard. It's only indirectly talking. And what this means is that this is not going to work, and I will have to do much higher loops, and therefore the effect will be much smaller than this value. Okay, but then the challenge, and this is a work I have done with my 2 colleagues from Spain and Canada, is to see, okay, I put this CP violation in the secluded sector, okay, how I transfer to my sector, because at the end I have to have the matter-antimatter asymmetry here. Okay, so what do we do? And this is the picture, okay? So we have the secluded sector. It's the dark sector because it's where dark matter lives, okay? And we have the standard model sector where we live, okay? And so we need to have a new force of nature. This new force of nature is, for example, in this example, which is a good example, is some gauge lepton number. And there is a gauge boson with Z prime that is going to connect the dark sector with the standard model. So the dark sector with us. There is also a singlet that is talking to the Higgs. Again, this is similar to the previous example. And this singlet is going to do two things. First of all, because it talks to the Higgs, it's going to do the same as before, give us a strong first order phase transition. Okay, in a quite a bit more involved way, but it's the same idea. So we are going to have a strong first order phase transition because of these interactions. And then this guy here, because on the bubble wall, again, here is the wall, but it disappeared from this slide. I'm sorry, there's a wall here. Okay. This profile, so as the singlet turns off when the wall is here, and the Higgs turns on, so the Higgs turns on, and the singlet turns off. This singlet has CP violation and talks to the dark matter and creates this asymmetry, this charge parity violating asymmetry in the dark set. Okay, so the singlet, this strong first order phase transition and sources CP violation in the dark set. Then we have this new force of nature that connects dark matter with the leptons, the electrons and the muons in our sector, and transfer the CP violation from the dark sector to our sector. And then once the CP violation is already in our sector, the spirals come and do their job. The same as before. Okay? But you need to have, so the new particles are the new force carrier, the singlet, and the dark matter. Okay? Of course, this is exciting because we are going to be able to look for all these guys. And that's what makes this interesting as a field. Okay? So, doesn't matter all the details. This is my team, all ladies, so I'm very proud of them. Actually, these are students and postdocs. And so let me just say that we are going to look for the set prime. We are going to have, as I said, a higher level of quantum corrections. We are going to be able to measure at electron dipole moment experiments, like my colleague at the University of Chicago, is doing this experiment, ACME. We are going to have this scalar, and we are going to look at this scalar at LHC before the end of the run. We are going to have deep underground experiments. We have like xenon 1 ton and LZ, which is going to look for the dark matter. Okay, and we are going to have gravitational waves. So all in one, so to say. So let me just show you one example before I finish. So here is the mass of the set prime as a function of the strength of this coupling to the standard model leptons. All these points here of all colors, okay, are points that give us the right matter-antimatter asymmetry of the universe and can explain the dark matter radial density of the universe. But only the red points are the ones that are allowed because of the searches of direct dark matter detection at xenon 1 ton. Okay, these gray ones, actually the LEP collider that used the collider when I was at CERN in my youth, in the same tunnel that we have the LHC now. Okay, the LEP collider already in its early times, without knowing about this theory, but you have to use experiments data, is killing all these gray points. And xenon 1 ton, the direct detection experiments where we, direct detection, we have some experiment where we have our detector and we hope that our matter will come and hit the detector and produce a signature. This is killing now these blue ones. And this is another view of the same points. But basically, this line is, roughly speaking, with some caveats, what the xenon 1 ton experiment has excluded. And in the next decade or so, xenon 1 ton and LC will keep pushing the boundaries of direct dark matter detection cross-sections, and they will come and test, hopefully find, dark matter that is. So finally, at LHC, we are going to look for these singlets, and these singlets are going to decay into this set primes, not set zero. And if you see here, again, red points are good, and diamonds have been already tested by the current run, sorry for the not being very clear, 13 TeV at 139%, LHC. Okay, but LHC will be probing all these points, and it will probably be probing these points with the new techniques I will
talking to you before, that is searching for particles that are produced, live for a while, they can live like 100 meters or so, and then they decay in the detector further away. And these long-lived particles, to see these long-lived particles, experimentalists have thought about many different ways of using the detectors in new ways, very innovative. Okay, and finally, gravitational wave signatures. So as I said, they are after the collisions of the bubble. They produce gravitational waves, and they also produce sound waves and turbulence after the collision of the bubble in the plasma. And if you do the calculations, and these calculations depend on some parameters, so they are very complicated, let me put it that way. It depends on parameters like the velocity of the Waggle wall, the time, the time of the phase transition, how long it takes the phase transition, how much energy the phase transition gives into the plasma. Okay, so there are all many parameters, but here all these green lines here are what we expect in this model, and these lines here is what this future gravitational waves detector can probe. Okay, so there are some regions of interest. So to finalize, this is some advertising, I guess. But so this is, I told you that in reality, when you have to do things properly, and this is something that we are starting to do now, and my team has been leading this effort, I talk about the critical temperature and the nucleation temperature. The real thing is the nucleation temperature. So you need to be able to see the bubbles nucleate. And when you do that calculation, the calculation is much more complex because you don't look at the potential and the vacuum structure. You have actually to look at what is the path, the minimal path that connects the two bubbles, the true and the false vacuum, and compute the nucleation temperature and compare that with basically the tunneling rate with respect to the inverse of the gravity. So if you do that calculation, you realize that things are much more difficult, and this is a team with whom we pioneer this work. Okay, and we want to go further. And there's one gentleman here that I realized I forgot to put, Mike. So my group plans to complement this analysis that are perturbative calculations with quantum simulations that we have started to do to shed light on this temporal evolution, on this non-equilibrium dynamics really, that happens at the phase transition. Okay? And we are, this is this next 10 to 20 years of plan. So to conclude, the Higgs boson discovery opens up. Oh, I had to be touching this or I will go into outer space. I forgot. The Higgs boson discovery opens opportunities to search for new phenomena and uncover mysteries of particle physics, like dark matter, antimatter symmetry of the universe. So the Higgs field, as it turns on, I hope I convince you, provides a very appealing mechanism to explain the matter-antimatter asymmetry of the universe. And what it does, the requirements are a strong first-order phase transition and new sources of CP violation. And what we can do is look at signatures at colliders, look at signatures in direct dark matter, deep underground in direct dark matter detection experiments, look for CP violation signatures in future electric dipole moment experiments, and look for gravitational wave signatures. We really need to get all this information from experiment and dedicated theory studies, if together with, as I told you about quantum simulations and quantum algorithms, with innovations in theory, calculations, and modeling, to see if we can pin this model of electroweak baryogenesis. It's a long program involving a lot of super bright people, and in some ways is complementary to the program of electrogenesis, which also involves standards, which is the one that LBNF Dune. So we have electric on one side with the Higgs field. We have LBNF Dune with neutrinos on the other side. And maybe neither of them is the right answer, but that's the nature of science. We are testing our universe. Thank you.
Thank you, Marcela, for excellent talk. And congratulations, on a really well-deserved honor. You can see from this talk why Marcela is an outstanding scientist. You give us a lot to think about in terms of these deep questions and these exciting ideas, which offer us opportunities to really understand the mysteries of the universe. Very excited about that. And now we're moving to the Q&A portion, so people will get to ask questions about this. I am Glenn Crawford. I am Director of the Research and Technology R&D Division at the Office of Higher Deep Physics here in the Office of Science at DOE. And we've proudly supported Marcela's research at Fermi Lab for many years in Bureau of Physics, and also her great work in workforce development of STEM scientists and students over these many years. We saw pictures of in the talk, so we really appreciate that. And so we have a few prepared questions that we will get to, but first, we want to give an opportunity for those folks in the room and who are out on Zoom watching the live stream to ask questions for Dr. Carena. Bill Kilgore is here monitoring the Zoom, and we'll check in with him for questions from the audience. So if you're out there and you want to pose a question, please put it in the Q&A section of the Zoom. And
they're on the TV behind you.
okay, yeah. Right. So for those of you out there on Zoom, put your questions in the Q&A. And if you're here in the room, right, please stand if you're able when you give your question, so the folks on online can see you. Speak slowly and clearly so they can try to understand the question. You need to. All right, so we'll start first here in the room. Anybody who has a question? Yes, Karen.
So congratulations, you have been very actively in developing and maintaining international connections, particularly but not exclusively with the Latin American scientists, as well to outreach to underrepresented groups here in the US. Could you please tell us about what this outreach efforts mean to you and how they have enriched your research and your career?
Yeah, thank you for the question. Well, first of all, I really think that bringing together talented people from different areas and backgrounds is one of the big powers of science. So I have tried to use that in my daily research and activities. Important things for me were, when I first came to Fermi Lab, I started this program bringing graduate students from Latin American universities, and a few students came for several years, more than 10, for 6 months to Fermi Lab, and they had the opportunity to develop further their career. I think it made a difference in their career in many ways. At the same time, they enrich very much the talent at the lab. So I think it was, that taught me that was a gain-gain situation. And that taught me I could make a difference. So that was a very tiny effort, but that was a good effort, a good experience for me, because I saw that, very deeply. I think other things that have marked the way I feel about this outreach, so to say, for scientists, is, for example, I have been trying to support the efforts of Department of Energy and Fermi Lab in particular in bringing Latin American scientists to Fermi Lab experiments. And I have a very nice success story that I would like to share very briefly. This is related to Brazil and is related to the development, and I'm sure Gina knows a lot about it, to the development of what is called, so it's a light trapping technology that is called Arapuca. Arapuca actually in Guarani, that is Indian dialect of the region of Brazil. It means trapping birds in the Amazons, but we are here trapping light. And the point is that this new technology was developed at the university in the Sao Paulo state because they got real support, substantial support from the Sao Paulo funding agency. And that occurred after Fermi Lab team really expressed their interest and their value for the science that these colleagues were developing. And not only that, now this has evolved, and this Arapuca, which of course is being used at Dune and even in early phase now as SBND, the short-wave neutrino detectors, and it's being built by people in different universities and at Fermi Lab. But this also triggered a consortium between Paraguay, so Brazil heavy news, but also Paraguay and Peru and Colombia, also collaborating with Fermi Lab. So that was, you know, I think that taught me how important it is to, you know, we here, I think we need also to be validated by our collaborators around the world. But I think that we can do a lot by validating our colleagues around the world, and maybe in countries where they need that very much, so that they can develop their own facilities and collaborate with us in a strong and so that was, you know, two things that I could go more, but yeah,
Thank you for that. That's a very good example. So I'll turn to Bill. Do we have a question from online?
We have a couple. Let's see. So one is the Higgs mass appears close to a stability boundary, raising the possibility of that we live in a false vacuum. Can you comment on this and evidence for or against this imminent threat?
Pleasure. In fact, I have a slide, I cut it because I thought I had to cut down slides. Yeah, so in fact, this is very intriguing, okay? That when we look at the value of the Higgs mass and the value of the top quark mass, the result is that there is the quartic coupling basically goes to a negative value at some high field energy. And this means that at some point, there is a vacuum that is deeper than ours. And so we don't know if we only consider the particles of the standard model. And in fact, this instability is due to quantum corrections. So when we consider the effects of the top quark mass, is what happens. Well, I'm talking to Bill, but he knows that very well, but it doesn't matter. Since I don't know who I'm answering to, I am answering to you. So this is intriguing and tell us that there should be probably something beyond the electroweak symmetry breaking mechanism that we have. For example, if you think about supersymmetry, okay, that is a way to add particles that would help you stabilize that behavior. So until we know what is the real mechanism of electroweak symmetry breaking, it's too early to answer or to be, well, not to be preoccupied, because even if it is metastable, it will take to your great-grandchildren to something to happen, and the rate is infinity. But I think it's too early to be even preoccupied at that level, because we think that something has to explain why electroweak symmetry breaking occurs. And that's, for me, is the key question.
Okay, very good. Oh, that's easy. Yes, David.
David, so see you again. From in your first model, where you just introduced the scalar, did that solve the CP?
No, the first model is a simplistic model to show how easy it is to make the strong Poisson phase transition sufficiently strong. This is a singlet that is even is not a complex scalar. So the second model has a complex scalar. We also get a strong Poisson phase transition, but of course things are a bit more exciting. So the first model was to do a proof of concept that it's not so hard, and to change the strength of the transition, and that also even the simplest model, you can try to search for these exotic cases. This is simplified model. Yeah.
Okay, I think we have time for one more question. Jeremy.
To talk about follow up on Doreen's question, you've mentored a lot of diverse students in your career. What strategies do you use to encourage them, mentor them along in their path?
Well, I would say my strategy is I try as much as I can to be very hands-on, and what I mean with that is I sit hours with them trying to understand problems. Okay, that's what I mean with that, hands-on. Maybe too much, I don't know. I try to encourage thinking out of the box and not being shy about asking questions, even if they could be sounding like naive questions. Even the most naive questions, they are not so naive when you look at them more carefully. And I think that questioning, I try to tell them that questioning, assuming knowledge is the best way to do research. On the other side, I try to build an environment or work environment where people feel respected and valued, not only scientifically, but also as people. And so I try to be approachable and try to understand what are their needs, because they are very different depending on the background of the person. That's one issue about diversity. But what I could interpret like A, you would interpret like no way, and that could get tension. So I try to be very respectful, and I try to build an environment where we work very hard, but we work very hard because we are passionate about what we do, and we feel in a comfortable environment as much as I think that's what I could say.
Okay, thank you for that. And with that, we will bring this session to a close. Let's thank Marcela again. And we look forward to many more great things from you and your team in the future, and hope you'll come back again and let us know, what you learned.
Thank you again for all your support all these years.
Right.
All of you.
Right. Thanks to everybody who attended and online, and we will now conclude. Thank you, everyone.